Hi, my name is Varun Kumar. Today I am going to present our work on data augmentation. This work has been conducted with my colleagues at Alexa AI, Ashutosh and Una. Here is the outline of this talk. First, I will discuss different methods for text data augmentation. Then I will discuss conditional data augmentation, which is the main theme of this work. Then I will discuss our proposed data augmentation methods, which can be used with any pre-trained model. And in the last, I will conclude the talk with discussing some limitations of this work and how it can be extended. So let's get started. Why do we need data augmentation? For many tasks, we don't have a lot of training data, so data augmentation is one way to generate additional training data and improve the model performance. Even for the task, when we have decent amount of training data, data augmentation can improve the model robustness. So that's why data augmentation is an important field in itself. What are the different challenges in the text data augmentation? Unlike computer vision, where data augmentation is very popular, we don't see a lot of papers and researchers discussing data augmentation in NLP, because data augmentation in NLP is a very difficult problem. So now let's discuss why text data augmentation is challenging. In computer vision, there are many standard ways like cropping, blurring of images, which can allow us to basically augment the training data. In NLP, we can't apply such transformations as random word shuffling because it might lead to meaningless examples. Also, such transformations might not preserve the class level. Here I will discuss one such example. A small impact with a big movie has negative sentiment, and word shuffling might change it to positive sentiment. So it is not obvious how we can apply transformations which are going to preserve the class level. Let's discuss some of the standard techniques that people use for text data augmentation. So the first technique is EDA, which is a simple word replacement method. In EDA, authors show that one can replace words with their synonyms and can do well on text classification tasks. We can also generate paraphrases for training data to augment our training data. Machine translation is another way to generate training data for tasks where we have training data available in another language. For example, if I am doing tweet classification in Hindi, I can generate more training data by translating English Twitter data. Back translation is another excellent method for data augmentation. It is quite widely used in NLP research. In back translation, we can translate English data to, say, German, and then German to English to generate more data. The another popular method for data augmentation is pre-trained language model-based word replacement, where we basically mask certain words and we predict the replacement of those words. While not discussed in this particular paper, we can also apply various kinds of transformations in the sentence or word embedding space. In this particular paper, we will only discuss text space. Let's discuss some of the word replacement-based data augmentation method. As mentioned earlier, EDA shows that simple word replacement operations such as synonym replacement can do well in low source setting. However, one major limitation of EDA is that it ignores the context while doing word replacement. Contextual data augmentation is one way to overcome this challenge. In contextual data augmentation, we can use any pre-trained model such as BERT, to mask and predict tokens. By nature, BERT will replace tokens based on the context, as when predicting, it considers all the words which are not masked in the sentence. For example, in this example, the movie was, say, good. It can change the sentence to this movie was excellent. However, there are certain limitations to contextual data augmentation. It is not perfect. One major limitation of contextual data augmentation is that it might not preserve the class level. Consider a simple example. the movie was, and there is a mask token. Now we want to predict what is the replacement of the mask token. One might need to consider the category or the label information before making the correct prediction. For example, we have, say, two choices, excellent or bad, to replace the mask token. If my sentiment is positive, I want to replace mask with excellent. If the sentiment is negative, I want to replace mask with bad. If we are not providing level information to these models, it's very difficult to preserve this information because model doesn't have level information, so it doesn't know whether the right choice is excellent or bad. So now the next question is, how do we condition on class level as well as on the context? Let's discuss conditional data augmentation, which essentially solves the same problem. Conditional BERT is one such model which allows us to condition both on class level as well as the context. In conditional BERT, authors modified segment embedding with the label embedding to inject label information into the BERT model. However, this work has a major limitation. This work can be applied to only those methods which has segment embedding. For example, if you want to apply it to Roberta or T5 or bar, you can't apply this method because these model architectures doesn't have label embedding. So it's very difficult to modify this work and apply it to those methods where we don't have label embeddings. In our paper, we essentially tackle this problem, how we can design a data augmentation technique which is model agnostic, a data augmentation technique which can be applied to any kind of pre-trained model, which is not, say, dependent on the model architecture. So a generic way to condition a particular language model is to fine-tune it on modified training data set where we are appending class level to the training data set. So we can simply prepend the label to all training examples and fine-tune the pre-trained model with its default language modeling objective. And then the fine-tuned model can be used for training data augmentation using mask and predict technique. This simple technique does not make any assumptions about the model architecture and can be applied to any pre-trained model. So let's discuss how we can apply this simple technique to do data augmentation with different kind of pre-trained models. Broadly speaking, pre-trained transformation-based model can be categorized into three different categories. First one is autoencoder models such as BERT, which are trained with masked language modeling objective. The second class is autoregressive models such as GPT2, which are trained in autoregressive manner. And the third category is sequence-to-sequence models, which are trained on some denoising autoencoder task. In this paper, we discuss how we can use these three broad class category models for data augmentation. While there might be, say, other models in future which doesn't directly fall into these three categories, since our technique of prepending class level to training data is very simple, we assume it can be applied to any pre-trained model. So we first discuss autoencoder model. So in this particular paper, we talk about BERT when we say autoencoder model, but we assume that this is applicable to any kind of autoencoder model. So for fine-tuning our autoencoder model for data augmentation task, we can use the default training objective. Since we are prepending labels to training data, we have two choices for model fine-tuning. We can either add class level to the model vocabulary, or we can decide not to add it. Note that if we don't add class level to the model vocab, during fine-tuning, class level will be split into multi-BP tokens. For example, if I have a class level play music, it might be split into two different tokens, say play and music. In expand, we are expanding the vocabulary. So we will add a separate vocabulary token in BERT to represent play music as a category. The difference between these two models, BERT prepend and BERT expand, is simply how we are handling the new tokens. Also note that in BERT expand, since we are adding a new token, we initialize this embedding randomly, and we need to train our model a little longer so that we have a meaningful representation for this new token. So usually BERT expand takes more than 100 epochs to converge, where BERT prepend might converge in only 10 epochs. At generation time, we provide a sentence with masked word and predict the masked word to augment the data. Now let's discuss how we can apply conditional data augmentation to GPT-2 model. For GPT-2 model, we provide label name followed by separator token as the prompt for generation. In our experiments, we found that simply providing label name followed by separator token is not good enough to generate valid training data. And we found out that it is crucial to provide additional context. That's why we decided to use GPT context, where we provide first 3 tokens along with the label information as prompt. The next class of models are sequence-to-sequence model. For sequence-to-sequence model, we use 2 different configurations, BART word and BART span. For BART word, we mask a word and replace with a simple mask token. For BART span, we mask a sequence of tokens instead of a single token and replace it with a single mask token. So the difference between BART word and BART span is that BART word is going to produce sentences which are of same length, where BART span can produce sentences which are, say, smaller or longer than the original sentence. Now, to evaluate data augmentation performance, we choose 3 different classification tasks. SST2, which is a binary classification task, SNPs and track, which are multi-class classification tasks. In SNPs, we have 7 different categories, and it's an intent classification task. SST2 is a sentiment classification task, and in track, we have question classification task, where we have 6 different question categories. For simulating low data regime, we sample 10 or 50 training examples and 10 dev samples from each category. For testing, we use full test data. All the results that are presented in this paper, we have conducted 15 different experiments, and we are reporting mean and standard deviation for each experiment. It is also important to note that for every experiment, we are randomly sampling data every time. Now let's discuss the baselines that we are using. So for this particular paper, we use 3 different text augmentation baseline. EDA is a simple word replacement method, as discussed previously. The second baseline that we are using is back translation. For back translation, we use English to German and German to English models. These models are provided by Fair Sequence package. And the third baseline that we are using is conditional BERT model, as discussed before. Now for augmentation, we are generating 1 synthetic example for every example in the training data set. And for classification, we are using a BERT classifier, which is based on BERT-based uncased model. As a metric, we use accuracy to report the classification performance. So here we present all methods classification performance. And here I will be discussing few important results. So first thing to note is that for this experiment, we are using 10 training examples per class. As shown in this table, BART-based method outperforms all data augmentation techniques, including the baselines as well as other pre-trained augmentation methods. We also observed that CBERT, BERT prepend, and BERT expand performance is very close to each other. It's interesting because while CBERT and BERT relies on some architecture change, for example, in CBERT, we need to modify the segment embedding. And in BERT expand, we need to modify the BERT model vocabulary. In BERT prepend, we don't make any change in model architecture. we simply use the pre-trained BERT model as it is and simply fine-tune it on modified data. Since BERT prepend doesn't require any kind of change in the model architecture, we think it is the preferred choice over other ways to condition model for data augmentation. We also note that back translation is a very strong baseline. It outperforms CBERT and other pre-trained based data augmentation techniques. We also measure how well the generated data is able to preserve the label information. For this experiment, we trained a classifier using old label data in order to perform accuracy tests on the generated data. While BART outperforms other methods in terms of classification accuracy, it is not the best method in terms of fidelity. What does it mean? It simply means that some of the generated data in BART might not be able to preserve the class information, though it is still doing really well in terms of classification accuracy. We also note that back translation is a really strong method in terms of fidelity, which also shows or underlines that state-of-the-art translation methods are really good in terms of preserving the class information. So here we summarize the key results from the paper. The first thing that we want to highlight is that prepending labels to the training examples is an effective method for conditional data augmentation. The best thing about prepend is that it is very simple. It doesn't require any change in the model architecture and can be applied to theoretically any pre-trained model out there. For example, one can pick a model from Hugging Face transformers package and they can apply this transformation and data augmentation method to any of the model. We also observed that sequence-to-sequence BART model outperforms other methods in terms of classification accuracy in low data regime. Now we discuss some of the limitations of this particular work and how it can be improved upon or extended. So the first limitation of our work is that we use the same set of hyperparameters such as masking rate, learning rate for all three data sets, which might not lead to the best performance for all considered tasks. It is very much possible that we might need different masking rates to get the optimal performance for a given task or model. While not covered in this presentation, we also found that if we use 50 examples per class, we don't observe any gains in pre-trained classification, in pre-trained BERT classification accuracy due to data augmentation. So it is very challenging to improve performance of these state-of-the-art classification methods in rich resource setting. So for high resource setting, it is not clear if data augmentation is going to provide any additional gains. The another limitation of our work is that we are only generating one example per training example. It might not be again an optimal setting. It is very much possible that one can improve classification performance by generating additional data, say 5 examples per training example. We leave these data points for future research. We hope that NLP community can benefit from our findings and improve upon our work. Here are a few references that I used in this presentation. Thank you for your time and listening to our presentation. Please reach out to us if you have any questions. Our code to replicate these experiments will be provided on GitHub. Thank you very much.